And the last thing I want to do is actually go through a more specific example of how we can think about using these this kind of machine learning approach for a real data set that we might look at as urban planners. And this data set actually is built into scikit-learn. It's one of their example data sets. There's like about 10 data sets they include to test algorithms on. They're like canonical standard data sets. One of them is the Boston housing prices data set, which has 13 features of different houses, and then the average market price of that house. And it's a 13-dimensional data set, but I've just used two features so we can visualize this the same way. So here we have the number of rooms of each house, and here we have the distance to an employment center, and the color is the average market value. Red is low value, green is high value. There's a two-dimensional data set. Again, like we can train based on all 13 dimensions if we want to. Just to visualize this, I'm going to pick two, and then we're going to train models to try to predict the average market value based on those two criteria. You can see there's some kind of spatial relation, right? Red ones are more towards this side, green ones are more towards this side, and I did this on purpose. A lot of the point of machine learning is actually doing a higher dimensional data sets where you can't just visualize it. But in all of these slides, none of these are real applications because we can see it visually. But it's important to see how the actual algorithms are functioning. So we choose these low dimensional examples. Okay, so is this clear to everyone? All the colored points are going to be our training points, so that we reveal the values to the algorithm so it knows these colors. It's going to train a model based on those. All the crosses are our validation set. It's values I've kept away from the algorithm. We're going to use that to validate our algorithms or our models. Okay, so here's our C and epsilon. Again, these are our parameters on the model which tells it how complex to make the model. And what I did here was set up a grid where I vary the C parameter. This is the general penalty, and the E, which sets the boundary of the soft margin. And I've run all 9 models. This is a very typical way you would make these models. You select some range of both set up. But you do a double loop, and you just set a range for both parameters, and you run every model. And what you're doing in each case is just getting the mean square error. You take all the points, and you see what the model predicted, and you see what is in the data set on the validation set, right? Just on those crosses. You see how the models vary. This is just a visual representation of this surface. This is sort of like the interpolation. It's basically predicting what the value is at each point. Okay, so here the red is the low values and the green is the high values. Again, even if we could visualize this, there's no real good way, just by looking at it, to say what's a good model, right? They all seem pretty good. But of course, we can do the validation. So the mean square error here is 24. When you get the slides and zoom in, you can see their error values. I printed them out for each example. This is the lowest one. And I picked these ranges on purpose to get the one in the middle to be the right one. But you really have to look through it. You have to tweak them until you get the best one, basically. You set up your own workflow for that. So this is the best model based on the validation data set. You can see what the model looks like. Okay, because this is a very noisy data set, and we chose only 2 parameters which don't necessarily describe the data in the best way. It uses a lot of support vectors, and this is a very complex kind of model. Okay, and this is the same exact data set, but actually that was a regression, right? So we did a continuous prediction of prices. We can look at the similar application in terms of classification. All I've done in this case is take the same data about housing prices, but I just made 2 categories. Either it's below 20,000 or it's above 20,000. All right? Now I have 2 categories. The red are higher than 20,000 value, and the blue are lower than 20,000. And here I'm running the same exact algorithm, but this time it's a classification to try to derive the boundary between those. So this is a typical kind of visualization of a regression. It's a continuous kind of surface of values. And this is the kind of representation of a classification. It's just a line. This is more like how we introduced the support vector machines. So it takes all the data and tries to draw a single line that splits one category from another. All right, so again, these are all seem like pretty good models. Of course, we can do validation. In this case, the error is not mean square error, even though I've labeled it incorrectly here. This is a general error, basically a misclassification error. These are literally the number of points that were misclassified. In classification, it's much easier to derive error values, right? Because it's either right or wrong. Like it either put in the right category or it didn't. And this is 34. This is the lowest number of misclassifications among all the models. So we say that's the best model. In the validation set of like 200, it misclassified 34. It's not great performance, but it's the best model out of the ones we've tested. So we take this as our model. Okay? This is one thing to realize right away, is you're never going to get perfect accuracy. It's not the point. Because we always deal with messiness and noise.